Okay, so now we've understood the idea of Jacobi's method and the Gauss-Seidel method, and we've understood why it's useful in particular situations. Now let's think about how we can represent both of these methods using a matrix. Just like with the Gaussian elimination, we broke down Gaussian elimination into LU decomposition, which is basically a matrix model for that particular method of Gaussian elimination. Okay? So let's suppose that I have a matrix representation of a linear system of equations that looks like this. Now you've probably seen this loads of times before, so I don't need to describe this too much. But just to highlight, these are coefficients. This is my coefficient matrix. This is a vector of known values, and x1 and x2 is a vector of values that I wish to find. Now when I expand this out and I get my system of linear equations, using Jacobi's method, these are the system of equations which I write, or the equations which I can write down. So x1 is equal to this, so basically using the top row and rewriting it in terms of x1. x2, again, rewriting the second row in terms of x2, and x3, rewriting the second row in terms of x3. Now just remember that there was a key difference between Gauss-Seidel and Jacobi's method. Jacobi's method, of course, was saying that all of the numbers on the left-hand side are my new values of x1, x2 and x3. All the numbers on the right-hand side was using the old values, strictly old values of x1, x2 and x3. So in other words, just to highlight that, I'm going to say that all of the numbers on the right-hand side are the numbers of x1, x2 and x3 at the kth step. So I'm just simply showing that with a little k in brackets next to that x1, x2 and x3. And likewise, all of the x1, x2 and x3 are going to be my new values, so it's going to be at the k plus 1th step of my Jacobi's method. Okay. Now clearly what I could do here to tidy this up is multiply both sides by this denominator. So in other words, multiply both sides by a11 in the first case. So this becomes a11 over here. And I've got the right hand side. Again, the second equation I could multiply through by a22. And the third equation I could multiply through by a33. Now the reason why I want to do that is because I want to see where the a's and the b's are and the x's are actually in terms of my original matrix representation. Okay, so hopefully you can see that all of the numbers on the left hand side, the a11, a22 and a33, are all the numbers which appear on the diagonal of this matrix. Okay, so in other words, what I could do is I could represent the left hand side by saying it's the matrix a11, a22, a33. All of the other elements can be 0 because I don't care about those elements. And I'm going to multiply it by x1, x2 and x3. Crucially, those are the x values at the k plus 1th step. So in other words, it's a vector of values at the k plus 1th step, okay, multiplied by what appears to be a diagonal matrix formed of the a11, a22 and a33, which is the diagonal of the original matrix or the original coefficient matrix that we had up there. Okay. If I look at the right hand side, well, okay, first of all, I just have b1, b2 and b3, so that's nice and easy. It's just simply my known value vector. But then I'm going to take away. Now, if you have a look at the right hand side, hopefully you convince yourself that those are all being multiplied by x1, x2 and x3 at the kth step, okay? And hopefully if you look carefully enough, if I put this all in one big bracket, I can basically form this as a lower triangular matrix, in other words, strictly lower triangular. So in other words, I could just have my A21, A31 and A32, and all of the other elements are 0, multiplied by x1, x2 and x3 at the kth step, added to my strictly upper triangular matrix. In other words, just zeros along the diagonal, zeros in the lower part, and just A12, A13, and A23 as this matrix times by my vector of known values. So x1, x2, x3. Sorry, my x values at the kth step, I should say. So they're going to be at the kth step. Okay, so hopefully you can convince yourself that that entire left-hand side of my, or this part in particular, can basically be written like, let me move myself out of the way, can basically be written like this. Okay, so hopefully you can convince yourself of that. Now the reason why I want to write it like that, the reason why that's very important to me, so I'm just going to write it on the screen, there we go. The reason why that's important to me is because this is just the diagonal part of my original coefficient matrix A. So in other words, I could just say this is the diagonal part, where the diagonal, which I'm calling D, is just simply the diagonal of my original coefficient matrix. Similarly, this part, the x1, x2, x3 at the k plus 1th step, is just a vector of values. So I'm just going to say the vector of my x values at the k plus 1th step. And that should be equal to, well, okay, I can nicely just call that B, because that's just a vector of known values. So I can just call that B. Minus, okay, what have I got in here? Well, basically, this is a lower triangular matrix. I'm just going to say that's L. Plus some upper triangular matrix. I'm just going to call that U. Times by my x values at the kth step. So in other words, I'm just going to form a vector of my x values at the kth step, like so. Okay? So basically, I can write this as a matrix representation form. Now you notice that D, L and U, particularly L and U, we've seen L and U before with Gaussian elimination, the LU decomposition. That's different. So the L and U in LU decomposition of that Gaussian elimination, that's different to what we're talking about here. Here, the L and the U, the L in this case is just going to be that part of the matrix. The U is just going to be that part of the original coefficient matrix, and the diagonal is just going to be that part of the original coefficient matrix. In other words, we're not using Gaussian elimination or anything to find L and U. In this case, the L is just going to be that lower part which I've circled in red. All the other elements go to 0. The U is going to be that bit which I've circled in blue. All the other elements go to 0. And the diagonal is just that bit which I've circled in green. All the other elements go into 0. In other words, you can literally just read L, U and D off from your coefficient matrix. You don't have to do any work at all. Now, just because this is looking a little bit messy, namely I want to find x to the k plus 1, not d times by x to the k plus 1, I could, if I wanted to, multiply both sides by the d inverse. Now, if I do the d inverse, I basically get x to the k plus 1, that's what I want, the x values at the next step, should be equal to d inverse times the entire right-hand side. Now, just because this is looking a little bit messy with negatives going on, what I could do if I wanted to is write this as L plus U times by x at the kth step plus my b vector. Okay. Now, you might be saying, well, hang on a minute, there's a negative which is off there on the right-hand side. That's not equal to it. Well, it's fine, because what I can do instead is I can say, look, my matrix A can be decomposed into a diagonal matrix, a lower triangular matrix and an upper triangular matrix. Ordinarily, I would have to add those three matrices together. Okay, that's just literally how I've reread it off up there. However, just because I want to get rid of these negatives and stuff which are going on the right-hand side, just looks messy to me, I'm just going to basically say, make L the negative of whatever it was before. Okay, and the same with U. Okay, so it'll be that as well. So in other words, the L and U will just be the negative of whatever's currently in that matrix A. Okay, we'll do examples of this, don't worry about that. But basically, I can produce Jacobi's method by writing it like this. So this is the matrix representation or the matrix form of Jacobi's method. If I want to do a very similar kind of thing with the Gauss-Seidel method, I need to be a little bit more careful. So again, I've just rewritten those equations down, which I formed before. I've already pre-multiplied through by that denominator, so it's pretty much at the step which we got to before. However, now I need to be careful about what my x values are at each step. So clearly in the first step, my x1 on the left-hand side is xk plus 1. And in fact, all of my x values on the left-hand side, they're all my new values. So I'm just going to write them all as xk to the k plus 1th step. However, I need to be careful about what the values are on the right-hand side. In the first step, the x2 and the x3, the first equation, the x2 and the x3, they're both values at the kth step. In other words, they're old values. However, I need to be careful when I look at my next equation, because whilst my x3 is still my value at my kth step, my x1 has become my value at the k plus 1th step. And similarly, in my last equation, both the x1 and the x2 are the values which I found at the k plus 1th step. Okay, because in other words, the Gauss-Seidel is basically using the most recent values of x1, x2, and x3. Okay, so it basically means that when I form my matrix decomposition, I can basically still write my matrix on the left as A11, A22, and A33. So that's just my diagonal matrix, just like I formed before. And again, I'm still going to have my matrix my vector x1, x2, and x3, crucially at the k+1th step. That's fine. However, I need to be a little bit more careful about what's going on the right-hand side. Okay. So again, I'm still going to have my B matrix. Let me just zoom out slightly so I can fit it in. So I'm still going to have my B matrix or B vector on the basis that a vector is just an n by 1 matrix. Okay. Minus, now I need to be a bit more careful because you can see that some values are k+1, my x values at the k+1th step, and some values are my x values at the kth step. So basically I can say that this is just going to be, it's going to be my lower triangular matrix, so 0, 0, 0, 0, 0, 0, but with A 2, 1, A 3, 1, and A 3, 2, times by my x values at my k+1th step, so x1, x2, and x3, all found at my k+1th step. And then plus, well, my upper triangular matrix is going to be basically the coefficients of my x values at the kth step. In other words, I'm going to have plus, again, an upper triangular matrix, so 0, 0, 0, 0, 0, 0, but my values A1, 2, A1, 3, and A2, 3 are going to be the coefficients of my x values at the kth step. So x1, x2, and x3 at the kth step. Okay, so if we figure this out then, right, so what have we got? Well, again, we can write this matrix as the matrix D, so it's just diagonal matrix. I'm going to have D, times by my x values at the k+1th step, should be equal to my vector of known values, that's just B1, B2, B3, minus, well, okay, I'm saying this is my lower triangular matrix, let's call that L, times by my x values at the k+1th step, plus this here I'm going to say is my U, part of A, so U of my x values at my kth step. Okay? So hopefully that makes sense. The only difference, of course, between Jacobi's and Gauss-Seidel is the fact that we're using the most recent values of x. Okay, so this should be true, and hopefully you can see that from the equations that I've got up there. Okay. Now again, if I just have a look at this, I'm going to get all of my x to the k+1th values, so the x values at the k+1th step, on the same side, because that's what I'm trying to find. So in other words, if I just rearrange this, I find that the d value times the x at the k+1th step, so I'll just keep it as k+1th here, plus my L values, my x values at the k+1th step, should be equal to, okay, it's going to be negative U times my x values at the kth step plus B, like so. Okay, so hopefully you're happy with that, just simply by expanding this out and moving everything which is times by the x values at the k+1th step onto the left-hand side. Now again, I could factorise this left-hand side to say it's D plus L, so the matrix D plus the matrix L, times by my x values at the k+1th step, should be equal to negative U x values at the kth step plus B. So clearly if I multiply both sides by D plus L inverse, I end up with this. So x values at the k+1th step should be equal to D plus L inverse, because I've multiplied by D plus L inverse on both sides, which is how I've managed to get rid of that D plus L on the left hand side, times by negative U times my x values at the kth step plus B. Now again, just because I don't like the fact there's a negative U in there, that's kind of a bit awkward, what I can do to get around that is just change that to a positive and change that to a minus. If I say that my A values, so my coefficient matrix, is decomposed to a diagonal matrix minus my lower triangular matrix minus my upper triangular matrix. So that's just a nice way of getting rid of those positives and negatives and just making it all fall out in the wash. So I'm going to call that my Gauss-Seidel matrix representation form. Okay, so this is the matrix representation form of the Gauss-Seidel method.